Hi there. In this video, I'm going to show you how to make a quantization shader in Unity's high definition render pipeline using shader graph. So first, let's get into what exactly I'm talking about. So quantization, which is similar to posterization, which can also be referred to as banding, basically is when you take an input image and you reduce the number of output colors. So I got this test image from Pixabay. It's a photograph of an owl against a blue sky by Veronica Andrews. I'll put the link in the description for it. And this is the original image. If we take a look at our histogram over here and go to, for example, the red channel, we can do a couple things to cause this banding effect, this quantization. First, we could go up to colors and posterize, and we can select an arbitrary posterization level. Let's go with something like 15. So before this happens, you will actually notice that the histogram demonstrates a variety of given values on this red channel. But after we posterize, you will notice that there are spikes on a much smaller set of colors over here. And that's because there are fewer outputs over the same set of inputs. And you will notice all this banding effect happens over here. You can do the same thing by selecting image mode indexed, and then you can change these settings here to generate a limited palette of colors. In this case, we're selecting a maximum number of colors of 256. And then once you press convert, it will find a good color palette and then display the result. And you'll see that there are much fewer colors that the image has to work with now. This is used in image compression and video compression to reduce the size of the file, because if there's less color information, there's less data to store. So how exactly does this work? Well, if we hop over to Desmos graphic calculator over here, we can take a look at it like this. Let's say an unaltered image is a graph of y equals x, where x is all of the input values and y is all of the outputs. So on a y equals x graph, the outputs directly correspond to the inputs. That's also called a one-to-one correspondence. So to demonstrate this, we can go over to our Blackboard here in GIMP, and we can say that here's the domain of inputs, just arbitrary values here, and here is the range of outputs. We'll call this x and this y. And there is exactly the same number of outputs as there are inputs, and that is a one-to-one correspondence here. But if we go back to Desmos, what we actually want to happen is we want to use a floor function. So if we take y equals floor of x, you'll see that the range is significantly reduced. So instead of there being an equal number of range values to the domain, the range is now severely limited. So what that would look like is this. So what ends up happening to the range of our graph is that we have all of these inputs on the domain, on the x-axis, and they end up getting mapped to a very restricted set of y values. In a normal floor function, that essentially changes the y outputs to be integers. So that's what we see here, is any values between 0 and 1 return a 0. Any values between 1 and 2 return a 1, and so on. Now, when we're working with color channels and brightness values, we're typically, in shader graph, we are working with values between 0 and 1. 0 being the darkest possible output and 1 being the brightest possible output. So let's add ourselves some constraints here to guide us. And we take our floor function, and before we continue with this, let's just make another quick observation. What is the range on the domain 0 to 1? It looks like it's just one value, right? A 0. Well, it's actually two. It's 0 and 1 over here, where floor of 1 will return 1, but it's only values of 1 that return a 1. The problem with this is that if you're looking at a shader graph, then only the brightest possible values in a channel are going to return a 1, and anything darker than that will return a 0. We can fix this by adding a 0.5 to our x value. This is essentially the same as creating a round function. The next issue that we have to tackle is that our outputs on this range 0 to 1 are very limited. Right now we're only getting 2 outputs. So to fix this, we're going to declare a variable, and we're going to call it n for now for number of colors. We'll call it 1. We'll restrict its value to between 0 and, let's just say, 255 with a step of 1. And we're going to change our function up here to be floor of nx over n. And what you'll see is that as we increase the n value, we get a greater number of outputs over our domain of inputs. So we're headed in the right direction. However, we should notice something as well. What we saw earlier was that this floor of nx plus 0.5 over n, when n is 1, is the same thing as floor of x plus 0.5. And when we did that, we found that we had 2 outputs, even though our n value for sampling is 1. So what this means is that when you input your desired number of samples, it's always going to be n minus 1. So we're going to change this variable to be q, and we're going to say that q is equal to n minus 1. Now when we select, for example, n equals 4, we will get 4 possible outputs because our q value is equal to 3. So what does this look like practically in Unity's shader graph? Well, as you can see, I've got a little scene set up here. I have created 3 quads. One of them shows the original test image. So what I've done is I've cropped it and reduced the size of it so that each side is the same size, and it is a power of 2. So it's 1024 by 1024. And in my input settings, I have selected point no filter so that we can see individual pixels. And I've also set the format to be RGBA 32-bit so that we have the maximum amount of colors. That's also sometimes referred to as true color. And RGBA 32-bit is pretty much the same as RGB 24-bit. We just have an extra alpha channel, which is 8 bits. You end up getting a total of over 16 million colors. That is the standard. That's where you find 256 colors per channel, because if each channel, R, G, and B, are 8 bits, 2 to the 8th is 256. So you get 256 colors per channel. That's the standard when you're opening up when you're editing an image in GIMP or Photoshop or what have you. So we're going to create a simple banding shader based upon this function that we just created. So we're going to go over to our shaders folder. We're going to create shader graph, HDRP lit shader graph. We'll call it simple banding for now. I'm going to add a 0 to the end of mine to avoid naming conflicts with some other shaders I have in here. Once that opens up, we're going to create a node. It's going to be a sample texture 2D. Out of that, we're going to create a texture 2D asset. Then we're going to convert that to a property. We're going to call it base. Then we'll connect its RGBA output into base color. And what this is in the context of our graph is this is our y equals x. So this fragment shader, this base color attribute of our fragment shader, that's going to be our y, and our base color is going to be our x. So then to create our floor of x, we're going to output this into a floor, and then plug that right into our base color output. Now to do our floor of 0.5x, we're going to plug RGBA into add, just plug it into A for now. We're going to pull this out into a float, and we're going to make this float 0.5. We plug that into floor. And what this would look like if we previewed it really quickly. So let's create a material off of our shader. You can leave it as the default name. Let's go to our simple banding quad, or whatever object you want to test this material on. And let's drag our test image into our base. And you'll see quickly that it is performing all these operations on an individual channel basis. So right now, since all it's doing is rounding each channel down or up, you'll see that we have a total of 8 colors here. This is basically the same thing as creating 1 bit per channel. You'd calculate your total colors by adding up the bits, the total color bits, which is 1 per R, G, and B, which is 3 total bits, and raising 2 to that value. You'd get 2 cubed, which is 8 total colors. Now, let's go back and continue our banding process. So we need our n value. We're going to create a float, and we're going to convert it to a property, and we're going to call this colors per channel. Then we're going to add this to a minus node. We're going to subtract 1 from it. In our original graph, we're adding 0.5 to our qx or nx value. We're going to multiply our x over here by our colors per channel, and then we're going to plug that in here to add 0.5 to it, and then take the floor of that. And then if you recall, we also have to divide floor by that value. So we can also just multiply by the reciprocal. That's fine too. And let's select the fast mode for the reciprocal method. Then plug our output into our base color, and make sure that you didn't accidentally select one channel. Save that again, go back to your scene. And you can see over here, and it's even more visible if we go over to our game view and zoom in a little bit, we'll be able to see that our colors per channel is working as expected. As we increase it, our bands become finer and finer, and we have more and more color detail until it's indistinguishable from the original. Now, if you zoom in your game view and you notice that everything is kind of jittering a little bit, and it's kind of like, it almost looks like temperature heat waves in the air, just go to your main camera and disable temporal anti-aliasing. You can use anti-aliasing if you want, like fast approximate, but temporal will create that kind of jittering effect. So just use either no anti-aliasing, fast approximate, or SMAA. Up to you. I'm going to go with no anti-aliasing for now. So there's one more improvement we can make to this simple banding graph, and that's if we go over to our colors per channel, we can set its mode to be a slider, and then select integer. We can make its max, let's say 256, its min 0, and its default value can be, let's just say 2. We save it and we go back over here to our slider, and you'll notice it's now integer values, and it creates a more predictable output. Lovely. Another thing you can do is you can take this 0.5 constant that we had and convert it to a variable, a property actually, and we're going to name that shadow bias. We're going to set its mode to slider. Its default value is 0.5 and its min is 0, its max is 1. And that way, if we go back to our scene, we can illustrate what we were looking at earlier. In fact, let's just go to Desmos real quick to look at it mathematically. This 0.5. Let's name this G for now, just arbitrary. We're going to restrict it to be between 0 and 1, and we're going to look at how changing this bias will affect the final output. So before we added the 0.5, it was just 0, and only values of absolutely 1 would return a value of absolutely 1. If we bump that bias up to 1, the opposite happens. Only values of absolutely 0 will return a 0, and any values above 0, between 0 and whatever your next step is, are going to return a slightly higher value. And so what that would look like in an actual shader in our material would be that if you bumped the shadow bias up to 1, the whole image becomes a little bit more washed out. The blacks become a little bit like dark gray instead. Whereas if you drop the shadow bias down, then all of a sudden your black point shifts. You could refer to this as black point as well if you wanted to. They're pretty much the same. Correct me if I'm wrong. But if you want to have a completely unbiased, balanced image, then you should leave it at 0.5. So now let's take this a step further with a more accurate quantization shader. If we go back to Desmos, so the problem here is that we're just taking a colors per channel. With actual quantization, since data is binary, we're kind of restricted to a power of 2. So we can take this Q value that we have here, and let's rename N to B. We'll restrict its value to between 0 and 8 for now. And our Q value, which we're also going to rename N for number of colors, it's going to be equal to 2 to the B minus 1. So that way you can see here that if you drop your B value, your bits per channel value, down to 1, you're going to get 2 colors per channel, because 2 to the first is 1. If you raise this to 3, you'll get 1, 2, 3, 4, 5, 6, 7, 8 colors per channel. And if you raise it all the way up to 8, and you counted all these, you'd get 256 total values in this channel. So this is the same thing as 24-bit RGB or 32-bit RGBA, because there are 8 bits per channel. So to implement this in Unity, we can go back to our simple banding. Let's duplicate this simple banding graph. Let's rename it to Quantization. Open it up in the shader graph viewer, and it's a very simple change. We're going to rename colors per channel to bit depth, or bits per channel to be more clear. So you'll take your bits per channel value and you're going to plug that into the B input of a power node. A is going to be 2 because we're raising 2 to the bits per channel. Then plug that back into your subtract, and that should be all you need for your quantization. Go ahead and save the shader graph, let it compile. And let's go to our quantization and create a material off of that. And I'm going to rename these real quick. Then go to your quantization, test quad, drag your quantization material onto that, and put your test texture onto the base map. So now we can compare these two. So I have them reversed so that you can very easily see their edges and see where they differ. If we go to our simple banding and select, let's say, 8 colors per channel, you can go to your quant shader and select 3 bits per channel, and it will get the exact same result because 2 cubed is 8. And you can very easily visualize this with other values as well. So our simple banding, if we wanted a full quality image of 256 colors per channel, where it's pretty much indistinguishable from the original quality, you can go to your quantization shader and select 8 bits per channel, because 2 to the 8th is, of course, 256. So now all 3 of these quads should be looking pretty much identical, which is more visible in the game view. There are no differences here. And if you wanted to compare your quant shader to your original, you can see where the quality begins to drop off. Oh, and really quickly, let's go back to our bits per channel and set the max to be 8. Or if you wanted to have deep color, if you had a monitor that could support that, you'd probably select perhaps 12 as your max. But 8 is the standard. Now, if you wanted to compare the output of the original against the output of the quant shader, then we can drop the bits per channel down gradually. We drop it from 8 to 7, and that's going to be 128 colors per channel. So that's going to be a much lower amount of data in the image, but there's barely any. But the 2 images are still hard to distinguish because there's enough data left over. Here's the border between the original highest quality and the 7 bits per channel image. If you drop it down to 6, you start to notice those bands appear more. 2 to the 5th, which is 32 colors per channel, that's going to be even more visible artifacts. 2 to the 4th, which is 16 colors per channel, that's the same thing as 12-bit RGB. Or 16-bit RGBA, and I believe this is the standard for GIF. I could be wrong. And if you drop down to 3, then 2, and then 1, and then 0, of course, there's no more color data. But Jack, you may be asking, what if I want my whole scene to look like this? Well, you've come to the right place. We can take this shader that we have and we can turn it into a custom post process in HDRP. So let's go to our quantization shader graph over here. We're going to duplicate it real quick, and let's rename it to Quantization Post Process. Then we can open that up, and we have to make a couple of small changes in order to get this to work. So first we're going to go over to our graph settings in the top right. If you don't see it, it's this info icon right here. And we're going to change the material under the HDRP dropdown to full screen. This is the same setting you'd use if you wanted to make a full screen custom pass. Then you're going to go over to here to your sample texture 2D and your base. And you're going to delete that because we're no longer working with a given texture. We're working with the entire screen. Then let's go to our HD sample buffer. Set your source buffer to post-process input. Then plug your output back into multiply. Once you're done with that, we have to do a little bit of scripting. So first let's create a mono behavior script. Let's rename it to Quantization Post Process. Once that compiles, let's open it up in our IDE of choice. Then go to the link that I provided in the description for the Unity HDRP documentation. So make sure to use the version of HDRP that is associated with your version of Unity. I'm using Unity 6.3, so I'll be using HDRP 17.3. So we're going to go ahead and copy this grayscale C# script. Then we're going to go back to our script over here. We're going to replace all of the template script with the one from the example site. Then we have to change some things. First, we're going to change the class name to match the file name. Then we're going to go to this attribute up here, which describes our volume component menu. So when you're creating your volume, you'll find this under post-processing/custom/ whatever name you give it. So instead of grayscale, we're just going to call this quantization. Then right here, this is where our public properties are going to be. You have to make sure to leave the intensity property here because every volume component requires it. Even though it doesn't really apply to ours, we're just going to leave it there. We're going to declare a public clamped int parameter. We'll call it bit depth. We'll set it to a new clamped int parameter. Its default value can be 2, its minimum can be 0, and its maximum can be 8, or 10, or 12, whatever you prefer. Then we're going to also create a new clamped float parameter, and we're going to call this our shadow bias. We're going to set its default value to be 0.5, its minimum to be 0, and its maximum to be 1. Then we're going to go down to the setup method. So this will initialize the shader. So first it's going to try to find the shader, but it's not going to be found under hidden/shader. By default, this shader graph is going to be found under shader graphs/quantization post-process. And you can paste that back down here. Now, finally, what you need to do is go down to this void render, and right under set float intensity, we're going to set the bit depth. We're going to do mMaterial.setInt bit depth.value. Similarly, we're going to do material.setFloat. We're going to set it to shadow bias.value. And you have to make sure that these strings exactly match the name of the references in shader graph. So to check that, you can go back into Unity. You can go to your shader graph over here, your quantization post-process, and you can select this bits per channel, and you can copy the reference. In my case, I am just going to call it bit depth, and shadow bias is just shadow bias. So we can confirm that they are the same as in the script. So finally, once that script is compiled, we're going to have to register our custom post process. Let's go up to Edit, Project Settings, head over to Graphics, and if you scroll down, you'll find that under this section, post-processing/custom, it does actually detect that we do have a quantization post-process, but it gives us an error that it's not registered in Project Settings Graphics. So just scroll down a little bit, go down to Custom Post-Process Order, and select After Post-Process, Quantization Post-Process. Now, some post-process effects that you create, you might want to have them operate on color values before other effects. So let's say you wanted to create a post-process that was specifically for the sky and objects, but before blurring. You would create that, you would set that to inject itself after opaque and sky. But in our case, we want it to happen after everything, so it'll be after post-process. Once you save that, let's go over to our scene, and I'll quickly create an ocean and a good-looking sky so that we can get an idea of how this post-process looks in an actual scene. Then you're going to want to make sure that you have a volume in your scene. So just create an empty and call it volume, and then add a volume component to it. Let's just create a new volume profile and add overrides. Go to post-processing, then custom, and then select quantization. First turn the intensity all the way up, then you can set your bit depth, and then you can change your shadow bias. And as you can see, we've already started to cause a lot of banding in our scene. If we look at the sky, we can see all these beautiful bands of color here. And as you adjust the bit depth, you will notice the colors get more and more restricted. It's a really interesting effect that I find is really unique. The only problem with it is that you tend to have a lot of washed out colors, so it's useful to also go ahead and add, for example, a post-processing and color curves, and then override that. Add a key, boost the saturation a little bit, and then add another override perhaps for color adjustments, and boost that saturation as well. And it will interact really nicely with this quantization effect. And as you can recall, we injected the quantization post-process after all the other post-process effects. So these curves and adjustments happen to the colors in the image before our quantization, which is why everything looks so lovely like this. Thanks for watching this tutorial. I hope that this is an effect that you can apply to your games as well. See you in the next one.